welcome back to Sugars Part 3. So this is going to be the final episode, thank God, in this sugar series. Alright, let's begin. So we can actually transform ketoses into aldoses. So this is called the Lobry-de Bruijn van Eichenstein, or I will call it LBE, because that's a mouthful, transformation. And it basically occurs in basic conditions. So take a look. So this is your carbonyl carbon, and we pretty much create a stereocenter there, and we turn this into an aldehyde. So what's the mechanism for that? Let's take a look. So it's actually not too bad. So the very first thing you're going to do is you're going to use your base, and you're going to deprotonate this. So we're going from the So here we're going from the aldehyde. That is very messy to the ketose, but the reverse reaction would work as well if need be. So from the aldehyde to the ketose, the first thing you do is you're pretty much going to form an enolate, standard enolate formation. You're going to kick up those electrons, deprotonate, kick up those electrons. Then this enolate is going to reorganize itself. You're pretty much going to just move the hydrogen over. So the hydrogen basically is on this oxygen instead of this one. And then the enolate is going to collapse down and grab a hydrogen to form a ketose. And to go backwards, it's you form the enolate and then you just undo what you just did. All right, so hopefully that makes some sense. So, and then to get from here to here, we saw that we can form the same exact aldehyde, and then all we do is we just swap where the hydroxyl is. The hydroxyl here is on the left, the hydroxyl here is on the right. So these guys are called epimers, if you remember, and so this is actually a useful way to do epimerization reactions. Okay, so hopefully that makes sense. So let's talk about reducing sugars. So what is a reducing sugar? In all honesty, reducing sugar is simply a sugar that has at least one hemiacetal. And so this basically allows them to react with metal salt. It can reduce the salts they give them a clear color change after this reduction. So there's a fun fact actually, like using Benedict solution, right? So for blood sugar, it relies on copper being reduced. And we'll see that in the next slide. But all we care about is this hemiacetal. If you have a hemiacetal, it's a reducing sugar. If you have an acetal, it's a non-reducing sugar. And both have their uses in nature. So there's a famous test called the Tollens test. And pretty much we just use silver and a little bit of ammonia. And this will result, if it is a reducing sugar, then we will get this positive test, this silver mirror down here. You can also look at failing solution and Benedict's test. But we care about Tollens test here. You're going to get the silver lining, but you're going to get atomic silver, or Ag0, and this is going to be your byproduct. So this will not work on non-reducing sugar. So this has to be a reducing sugar. So let's do some practice. So which one of these is a reducing sugar or not? So please take your time and think about which one is a reducing sugar or not. Let's continue. Okay. So on the left, we see, first find the anomeric carbon. Do we see a hemiacetal? We do. Reducing. Here, do we see a hemiacetal? We do. Reducing. Do we see on the anomeric carbon now? Here it's a little trickier because of the orientation is switched up. But which one do you think is going to be your anomeric carbon? It's going to be this one. How can I tell? Well, you find the ether, and then you're going to look one carbon on each side. So the one on its left has an oxygen attached to it, but the one on its right does not. So it has to be this one. And then going from there, we see it's methylated. So this is not a hemiacetal, but an acetal. So non-reducing. What about here? Well, it's the same principle. You're going to look here, the anomeric, and here. As you can see, this is an acetal, so this is non-reducing. And then what about here? So this is kind of a trick question. But you have 300 of these. And what are these? Well, you have an acetal here. The 300 acetals, and then you have one hemiacetal. So as a whole, is this a reducing sugar? No. But this is a reducing end. And this is not a non-reducing end. So this is important because, for example, in your body, glycogen has a both non-reducing and reducing end. So that's it. But in reality, we wouldn't call this a reducing sugar just because there's only one hemiacetal compared to 301 acetals. All right, hopefully that's clear. Let's do another problem. So let's characterize the following linkage. Is it a reducing sugar? So take a second and think about that. Okay, so this is a reducing sugar. Why? Take a look right here. You have your hemiacetal. Even though it's an acetal here, you still have your hemiacetal. And to characterize this, what type of linkage is this? Well, first find the anomeric carbon. So this is a 1. And then you're going to label what carbon this is. So this is 1, 2, 3, and 4. So based on the anomeric carbon, right, that's what determines the alpha or beta. If you have an anomeric carbon linkage, you're going to look at this one. You can see that this points up, and then this points up as well. So you have beta. Hopefully that makes sense. Let's do some more practice. So characterize this following linkage. And is this a reducing sugar? So here we have a glycosidic linkage between a furanose and a pyranose. But the same methodology applies. All right. So in this case, we can't just do the alpha 1,4 or a beta 1,4 or just the alpha beta notation. Here we need we need an alpha and a beta. Now why is that? Well, it's because the anomeric carbon for both is where the glycosidic linkage occurs. So we can't just say one takes preference over the other. However, we can number these carbons. So this is carbon 1. And this we are going to say is carbon 2. Now, why do we say that one's carbon 2? Well, in this case, we would say this is carbon 1 here. And this guy right here, this points up and this points down. So this is going to be your alpha. And this points down and this points down. So this is going to be your beta. Okay. Hopefully that makes sense. And so is it a reducing sugar or not? Well, this is an acetal right here. And then this is an acetal right here as well. So it's non-reducing. All right. Practice problem number 4. So remember from the previous one, so this is pretty much exhaustive methylation and then acid hydrolysis. What will be our products? So take a minute and draw it. Okay. All right, so let's go over this problem. So what do? First things first is you need to understand that all of these guys are methylated. So it's a little hard to do, but I'm going to be pretty much methylating every single OH out here. But assume that after I methylate every OH, what's the next step that I do? I need to break this linkage. Okay? So if you recall from the previous video, when we break the linkage, right, we break it at carbon 1 for both. So if this is going to get methylated, then in my Fischer projection, this is going to be in the hemiacetal form. Okay? Now the question is, what happens? Is this going to be up or down after breaking? Look at where it is in the plane. So this is pointing up, so I'm going to draw this as OH. And then this is pointing down, so this OH is going to point down. All right? So in this case, for the anomeric carbon here, it doesn't really matter because it's the aldehyde. So I'm only going to have one OH here, and that's this one that is non-methylated. So that is what the point I was trying to make in the previous video. Every other OH is going to be methylated except the one that is used to form this hemiacetal. And in the second sugar, that's one is also not going to be methylated. However, you're going to have one more OH that's not methylated, and it's the one at position number 4. Okay? So position number 4. So this actually should, this is an error. So this should be to the right. So, okay? So 1, 2, 3, 4. Position number 4. It's going to be on the right. The OH is going to be pointing down. So that's what we make. And then at 1, we kind of can't tell if it's going to be alpha or beta, but it doesn't really matter for the Fisher projection itself. All right, so once again, just going through this problem one more time. What do? First, you methylate on every single available hydroxyl. Then you hydrolyze at both carbon ones. Okay, so you hydrolyze at this one, and then you hydrolyze at this one. Both carbons, you hydrolyze. And at the anomeric position and at carbon 4, how do you know it's up or down? Well, it's what it is in the bond. So here, the bond I drew, it's very clear that this is up. So this was a beta. And then down here, 4 was down because it's below the plane. So hopefully that explanation makes sense. So I wanted to thank masterorganicchemistry.com for helping me make parts 1, 2, and 3. So thank you for your work, and thank you all for watching. Have a good one, and good luck on your exams.